So far in this module, we've looked at the physical structure of the binary tree, and we've looked at the data ordering requirements of a binary search tree. And now what we're going to do is see why those data ordering requirements make the binary search tree a really efficient structure for searching for data. On the left, we have the algorithm for finding data within the tree. And on the right, we have the tree we're going to be searching. And let's start by just walking through this a few times. We're going to look for the value 3, starting at the root node. And the root node is the node containing the value 4. So, that node is not null, so we skip that. 4 is not equal to 3, so we skip that. But the provided value 3 is less than the current value 4. So what we're going to do is now recursively call find, this time passing in the left child of 4, the 2 node. So now we start this process over again. Is the current node null? Well, it's not because it's the 2 node. Does 2 equal 3? Well, it doesn't. Is 3 less than 2? Well, it's not. So the last thing we can do is recursively call find, passing in the right child of the 2 node, which is the 3 node. So we say is current null? Well, it's not. And is the current value of 3 equal to the value of 3? Well, it is. So we return the 3 node. And there we've now found the value 3 within the tree. But notice that we did it only having to look at 3 nodes. Now imagine in a linked list, we could potentially have had to have searched all of the items in the list. Now let's find the value 5. Well, we start at the root node 4, and since 5 is larger, we need to go to the right. That brings us to 6. Well, 5 is smaller than 6, so we fall to the left, and we have found the value 5. But now let's look for the value 8, and this one's a little bit different. We start with the value 4, and it's larger than 4, so we go to the right. We get to the value 6. It's larger than 6, and it's larger than 7. Now from the 7 node, because the value is larger, we end up calling find recursively with 7's right node. Well, 7 doesn't have a right node. So current.right from the 7 node is null. So once we recursively call find, well, the current node is null, so we return null. And ultimately, the caller of find will get a null value back, and that will inform the caller that no value was found in the tree. But even here, notice, in the case where the value did not exist in the tree, we did not have to look at every node in the tree to determine that. We only had to look at 3 of the nodes. And that's the property that makes a binary search tree desirable compared to a structure like a linked list. In a linked list, the only way to determine that the value of 8 was not in the linked list would have been to have looked at every node in the list. So here we've been able to determine that nodes were or were not in the tree while looking at a subset of the data in the tree. And that's a very powerful mechanism, and one of the reasons that binary trees and similar tree structures are very commonly used in computer science.